Hi, everyone. Welcome to PIGgies. If you're new here, this is the Bay Area Python Interest Group. We meet in this room at LinkedIn the fourth Thursday of every month. And this group has been around for a very, very long time, since I think the late 90s. Or was it? Yeah, I think late 90s. Anyway, we have a great speaker tonight. Before we get started with our main talk, does anyone have any announcements or anything, like they have a job they want to offer, they're looking for a job, or some project they want help on? Or we'll have another opportunity at the end if you want, but anyone have anything? Okay, great. So anyway, our speaker tonight is Alex Martelli, and we're really always excited to have him come speak. In addition to being a Googler, he's, I think, a fellow of the Python Software Foundation. He's received awards for his Python work. He's written books on Python, edited books on Python, and every time he talks, it sounds like a very basic topic, what he's going to talk about, but he has a lot of insight, and I really enjoy his talks every time. So, and we're the first audience to hear this talk, I hear, so I'm very excited. So everyone give him a quick round of applause. Thank you.
Welcome, everybody, and thank you for the unexpected full house. Yeah, when I came to interview for the job at Google in 2004, the then organizers of PIGgies did me the great honor of asking me, since I was spending the right days in December in Mountain View, to if I could do a presentation, and since then I don't think there's been a year where I haven't done at least one or two. And yes, they're all on basic stuff, because I hope that basic stuff is of more interest to everybody, and that if we look at it real hard, we can get more insight, or at least that's the hope. And in this particular case, I believe that is the first time, on my request and with permission from the organizers, using PIGgies as my Guinea PIGgies for this talk. Normally, I prepare a talk, I give it to friendly audiences, like within Google, and then it debuts in some big conference, and then I give it at PIGgies, and then some other big conference. This time it just didn't work. With Google Next, no other Googler had any time to listen to talk, and I didn't have time to give it because I was working at Google Next too, and so on and so forth. And the first major conference is 2 weeks from now, is PyCon Italia 8, the 8th Python Italia conference, and this will be my keynote. And so, exactly because this isn't a talk I have prepared in depth and rehearsed as I normally do, please, my apologies in advance for any less than perfectly polished part of the presentation. But please do feel free, while we will have a Q&A at the end, of course, nevertheless, please feel free to interrupt anytime with questions or observations. I may or may not have the right answer. At the very least, I'll take notes. Actually, my wonderful co-fellow of the Python Software Foundation and wife, Anna, is going to be taking note for me. Thank you so much. And while this doesn't particularly help you guys, it will help the next audiences of the talk. So again, thank you in advance. All righty, so testing in layers. Well, it's pretty basic, testing. What do I mean by layers? That's what the rest of this presentation is supposed to say. The URL there is where I put the PDF version of these slides, so that I imagine the organizers also have a website for them, and I'll upload them when requested. The form of the URL suggests that these are the slides I prepared for PyCon Italia 2017, also known as PyCon Italia 8, in the English version thereof, as opposed to the Italian version thereof, just in case you're trying to decrypt that very mysterious thing. Well, to start understanding the layers part, let's diagram a somewhat typical software system. It's got components in some reasonably modern arrangement. Those might be microservices potentially running in distributed ways with some remote procedure call, but it doesn't really matter. Even if everything is actually linked into some kind of monolithic blob, we still have modules and packages. That's how we've been developing software, I hope, for 40 or more years. And of course, we are very aware of our dependencies and organize things so that there are no loops. There is no case, I hope we are all agreeing on this, in which component A depends on component B, B depends on C, and C depends back on A, because that's a nightmare of unrestrained proportions. So once you make sure your dependencies are a directed acyclic graph, DAG, you can always define layers. The algorithm to do that is known as a topological sort, but that's of no interest. You have a low-level layer, which are components with no dependency on other components. You have a middling level or more. You could have a very complex system. I would not recommend having more than about 3 layers, but hey, depends how complicated it is, what is it that you're trying to do. The middling layer are things that depend on possibly other middling layers, but also usually on the lower layers. And then the high levels, which depend on anything but the lower layers. That's how I prefer a 3-level classification, but it's not mandatory. We all agree that this is how things are organized. Sometimes people ask, what, you have multiple top levels? Well, why not? Maybe I have a graphical user interface and a command line interface and a API server, which all take requests for the same kind of work that my beautiful system is doing from different ways. Command line interfaces are far from obsolete. Whenever we release something that some new feature in Google Cloud that can only be accessed via the console, the GUI, the graphical user interface, we immediately get, very rightly, attacked by customers saying, so how am I putting this in my shell scripts? When is the command line interface version coming out? And of course, it's usually the next day, but the point is, command line interface is not dead. It's far from dead. Anyway, that's why I happen to have 3 top layers, because the GUI and the API server and the command line interface. But of course, I have very deliberately used extremely generic, like alpha, beta, gamma for the high levels, A, B, C for the middle, and 1, 2, 3, well, mostly 1, 2 for the lower. I've also singled out as adapters those components in my system which depend on components out of my control. I usually have some. For example, in this case, I'm assuming I'm going to interact with some data store that I haven't built, I call it a DB, or database. What I have that works with it is my database adapter. Whatever the nature of the DB, I don't control it. I'm actually not going to test it because presumably it's tested by whoever I have adopted it from or bought it from and supporting them. But similarly, I assume I'm using some DNS service I haven't written. I need adaptation for my specific system's purposes, but and I haven't actually committed of how do I do auth, which is a beautiful shortened version of both authentication and authorization, so it can be either or both. But do I do it all myself, or do I shell out to some auth provider? Whatever, doesn't really matter. Okay? So this is how we develop software. Well, this isn't the method by which to develop software, but this is how a typical system we develop and deploy today kind of looks like if you squint just right at the proper level of abstraction. How do we test it? Hey, we all know that testing is good. I'm actually a testing fanatic, but if anybody needs to be convinced that testing is good for you, I'm sorry, we'll skip the rest of my presentation and I'm getting into the spiel. No, I won't, but I should. Okay. Testing was not all that popular once. That was back in the bad old days when the only two ways to think of testing were known as white box and black box. Has anybody ever programmed in that mindset? The black box testing was supposed to be completely ignorant of the internal structure of the system, all based on what shows on the outside. Typically done by a separate quality assurance group, and often not even programmatic, but based on poor human beings banging out at a keyboard or a mouse and eyeballing the screen that right things would come out. Horrible job. And white box was presumably done by the developers in full knowledge and understanding of exactly how every line of code in the system was written. Which, if you think, why is this inferior? I've already criticized the black box side of things. The white box, it's, if you already know how it's written, it's so easy for your tests to end up essentially reflecting the exact same understanding that's already going into the code, in which case you're testing nothing. You're just saying the same thing twice and testing that you are saying actually the same thing. What's the use? The first suggestion to overcome this blockage, whereby only poor human beings trying out the system were testing it in any sense, was Weinberg. In The Psychology of Computer Programming, 43 years ago, he explained that when you know exactly the algorithm you've written, he had mostly in mind scientific programming, Fortran and things, but you already have in mind, because you've written the code, the formulas and algorithms in use. You are going inevitably to write tests that reflect exactly the same algorithms and formulas, and so are really testing nothing at all. The only proper way would be, he said, to write the tests before the code. When that notion, test-driven programming, was promoted 35 years later, people took it as new. Everything old is new again, right? Because, hey, who reads 35 years old books? I mean, programming books. Me. That's why I think I found this out. Anyway, the problem is that despite Weinberg's and Beck's and many other great contributions, the modern way ends up too close to the bad ancient way. Because nowadays, we don't call our test white box and black box anymore. I haven't seen the terminology around in quite a while. But we call them unit tests and integration tests. But often they tend to be kind of similar. The unit tests are white boxy. They're focused, they're tests by developers, for developers, of developers, you could say, to complete the quote. But so while properly done, they're absolutely precious. Are they adding enough value? And the integration tests are meant to be end-to-end. End-to-end is a very heavy thing. If you have infinite compute power, you could be running end-to-end tests every minute. But the reality is a little bit different. The amount of computing power at your disposal is limited. The amount of pathways to your code you want to test, you would like to test, grows exponentially. It's a combinatorial explosion. You are never going to have enough unit tests and run them fast enough. Just to prove my point, we just released Python 3.6.1. I believe that was for the release candidate, so 3.6.1 RC1, which was accepted, it was without any fixes, became 3.6.1. I think it was about a week or 10 days to the release date when our one of the greatest core contributors, Brett Cannon, announced, I have changed the project configuration so that passing the Travis tests is not required anymore to do commits. So be very careful because your commits, pull request, because we've just also moved to GitHub, but that's a different story. Be very sure your pull requests have been very carefully examined because they're not being tested. Why would Brett suddenly decide? Because the amount of Travis we are given for free as an open source project was such that if you had a fix that was supposed to go in and started the going in process, it wouldn't go for days because of the backup in the integration test. This is integration tests end to end. Nobody can afford them. If we had 100 times the Travis firepower, we could probably do, say, twice as many tests, given the combinatorial explosion, maybe 3 times. Still nowhere like enough. And if tests are such that at the crucial time before you cut a release, you have to turn them off because they never turned off the mandatory requirement that tests pass before the code goes to the code base, was it worth your time and energy to write those tests that you can't afford to run? That's the problem. It's even worse in those shops. I don't know many open source shops that work that way, where the integration test is still of the bad old QA variety with a human in the loop. Because, we can't automatically test a graphic user interface. It takes a human being to tell us if it looks good. That's not my point here. But obviously, you can't afford to do that before every release, or you'll never be releasing. What I propose, pattern language that I extracted observing the way people using some of the best practices are actually structuring their tests. Match the layers in your software with layers in your testing. Start with the unit tests. They are focused on being fast and run all the time. Many development environments have a daemon running that notes anytime you save a file, they rerun the unit test accepted by that file. That happens in the background, but it must be very fast, because if it takes 5 minutes before an alert pop up, hey, a commit you did 5 minutes ago was broken in the following way, you may have done other things in the middle. You don't remember anything anymore. Latency must be low, so the test must be fast, even if they run automatically in the background. So focus strictly on the internal logic of the module you're testing. Mock out every dependency. We'll be a bit, you do understand the concept of mocking and other fakes. We'll briefly mention it, but I'm not really covering it not in depth. But remember, fast above all. Now, on this base, you can build layers of other layers of test, all the way to end-to-end integration test, but all the missing layers in the traditional practice where there's only unit and end-to-end. Most of what I'm presenting here, I'm so sorry, this font has become a bit small. Anyway, it's the newest version of Apple Keynote, and I must have done something wrong here. The fundamental things do apply. So all the core principles of automated testing. All tests must be reproducible. There's no such thing as a test whose outcome you don't know in advance. So if there's any randomness in your code, make sure that when unit testing it, you force a seed to whatever random number generator, so make it repeatable. If you're using hardware random number generator, make sure you dependency inject a fake, like an algorithmic random number generator with a fixed seed. If it depends on time of day, day of week, or anything, if the results change depending on when the code is run, mock out, fake out the time-related system calls, and so on and so forth. I could, and actually did in the past, did many hours of presentation on the fundamentals of testing that I've seen people not do. Just one more thing. When you fix a bug, that's the time when test first is really the only way to go. Don't even start of fixing the bug unless you have a test, a unit test, that if it had been in your suite to start with, the bug would have been caught by the test instead of propagating all the way to the user. Once you have the test that fails, then you find and fix the bug, and the test passes. That's absolutely the only way to go. Now, within this framework, which doesn't change, what is being specifically proposed here? Well, let's take one example. How do you test the database adapter? I put a little circle around the specific component I'm talking about. Well, first of all, you want to have pure unit tests that only check the logic, the understanding of your code, your adapter, and not the database itself. And for that, you mock it out. You mock out the database. And that is going to be perfectly fine if you are 100% certain that you understand the database completely. So, for example, suppose the database you're using has a constraint whereby after you've called close on a connection, calling or any other method on the connection, object will raise an exception. And you didn't realize that. So if you didn't realize that, You may have the bug in your code whereby in certain cases you try to do something else after closing, but given it's a problem of understanding, your mocking of the database will look like everything is fine, because the same misunderstanding is present in the mock or fake as in. So you need a second layer of unit tests, which are an integration test. Even though that's the lowest level module, it needs an integration test. Integration with what? With the outside component that's not in your control. It's not end-to-end, far from it. It actually uses the same code as the unit test, but it emulates the DB instead of mocking it. There's a big difference between emulation and mocking. It doesn't need to be anywhere close to a real usable production. If feasible, you can do a fake database in memory. That's perfect, because you're not going to put a million things there anyway. It's just to prove out the logic, but it must reflect the semantic constraints, the same semantic constraints as the real data store. So for example, if the close method must be the last one called, that must be checked and diagnosed as a problem in the emulated DB. So we'll get back to it, but this is the concept. The reusable part is that thing I put in a green box, the body of text. Like, how do I exercise my module? Making sure every part is well covered, every semantically meaningful if branch, and so on, with a certain body of text, which I typically write when I do my unit test. I mock out. I'm using the unit test mock from Python 3. I hope you're familiar with it. I'm not. But anyway, I prefer to always mock patch object, because if you mock patch a name, which is allowed, it's so easy to mock out the wrong name. It's happened to me so many times. I've started using mock patch object exclusively, and now I never patch names anymore. Autospec there is never any reason not to have it. If you're mocking out something existing, it only guarantees that all the methods have the right signature to the extent Python lets you constrain a signature. So number of arguments and things. You can't really do type constraints or something if the database has it. Pity. So it's a little more, it doesn't really check in any depth. It still doesn't cost anything. And of course, in a mock, you prepare the side effects. That is, the exceptions that get raised, or the results that get returned, and so on. And then you do the body of tests. Now, for your second layer integration tests, the body of tests need not change. You're actually doing the same set of work which exercises all the logic of your module. The preparation is completely different. Instead of patching in a mock object, you prepare the fake object. Presumably you have a fake DB module that fakes out your DB. You build it with whatever appropriate parameters. Mock patch object with new equals lets you inject that, stub that out. And then you populate it by executing, I don't know, insert statements or reading a file or something. Depends on how your thing works. And note that you have a full integration test ready. You only need to start, presumably local, or maybe the next machine next door, copy of the actual database with the expected population, and then you run just the same body of tests that you run for the shallow integration test and for the pure unit test. So that's the reusable element of the reusable layer. And the preparation parts are completely different, but the work that depends on your application, that is, what exactly does this DBA thing do, and how do I make sure I've explored all the meaningful paths, is the same in all cases. Note the difference between mocks and fakes. I strongly recommend starting with Martin Fowler's article. Is distinguishing mocks and stubs. It draws different distinctions, partly because Martin is typically talking about Java, Python's a bit different, but all the variety, dummy, fake, stub, spy, and mock, applies to any language. Because the core idea is who owns and maintains the thingy. In a mock or dummy, you do. So your understanding of how the thing you're mocking out is supposed to behave had better be perfect, because if you misunderstand, that's also reflected in the mock, and so your tests don't get the problem. The ideal situation is where whoever owns and releases the actual database code also releases the fake. That's a very difficult concept to get program managers to understand, as in, what, should I waste the engineer's time having they make a ridiculous small in-memory version of the database? Because it will have the same exactly semantic constraint as the globally distributed petabyte size database, which people need to be testing again. And that's why we're finally getting emulators for every major component in Google Cloud, one at a time. But I lead the mass market, the long tail technical support of Google Cloud platform, and I've been doing so for a few years. I've been hammering product managers relentlessly and finally getting through that, yes, this will reduce the number of errors by customers by a factor of 10. And by the time I've finished evangelizing them on how they should have tested before coming to support, a factor of 100. I apparently can be rather convincing. All right, anyway, on to what about a middle level? That's a bit different, right, from the low-level thingy we're doing. How do we test that? Well, we start with pure unit tests. Since MLA depends on LL1 and LL2, we can mock those. And it should mostly be fine because our team owns LL1 and LL2. The reason I drew it this way was exactly to say, okay, this is the software we've developed and maintained, release, and so on. So presumably, whoever's doing MLA and the tests has very strong understanding of all semantics constraints of LL1 and LL2. On the other hand, I've often found that it's fast enough to use the real LL1 and LL2, which would normally be the second layer test. But the point is, if LL1 and LL2 don't have external dependencies, unless they do very complex computation, they're not going to take all that much time. So it depends on what they're doing, of course. I can't know your application. But what I do is I try both ways, since the mocking shouldn't take me long, with a stopwatch, which is module time it in the standard library. I hope you're familiar on how to use it for micro benchmarks. If they're fast enough, if you know they're fast enough, you're familiar with them, and you know they do moderate amount of computation and no I/O, then don't even bother writing the pure unit test. Okay, the purists of testing, I hope, don't have any stones, or they would start throwing them at me. I'm an enthusiast of testing, not a purist of testing. I think that sometimes it can be okay to not mock out dependencies which are very lightweight and within your entire control. So this is the case. The same body of test. Of course, it's a completely different body of test from the other time. So I used this in Corel. And if you mock, you prepare the side effects. If you don't mock, you populate or prime the lower level modules if they need any. If they have any state or something, you set the state as expected. So in this particular case, where there end up being no external dependencies at all, it's actually simpler than the simplest case we'd covered before. And now, let's come to one of the top layers. If there are multiple independent top layers, you'll have to repeat that process for each of them. But first, for the pure unit test, you mock out the middle levels. All the middle levels it depends on, right? So B and C. For the second layer test, you want to use the actual modules B and C, but mock what they depend on. So in this case, you would, all right, I can't get a light out of this thing, apparently. It's a new thing. No, sorry. So anyway, you need to mock your adapter modules because you don't want to actually depend on the external systems. Again, as in the previous case, the LL2, which is a dependency of MLB, can be mocked, or if it's lightweight, fast enough, and understand very well, you can use the real thing and do a little bit. But now, of course, we have a third layer, because integration test can go all the way from the top to the low levels, including the adapters, and the external dependency, as in the previous cases, can be mocked or fakes. Or, as I mentioned, although it wasn't in the slide, they can use the actual code of the system and just run it against a small pre-populated thing. So, for example, you don't have, for an end-to-end test, to have a fake DNS lookup thingy. You can set up your own local machine or network neighbor. Just make sure it doesn't go out to root DNS servers and take forever. It just serves a little DNS zone from your own fake domain and things. Now, if you start counting all the paths, all the alternatives you have here, the combinatorial explosion problem starts rearing its ugly head again. There's so many things you could do. Which ones, plural, should you do? Unfortunately, I can't tell you because I don't know your application. But the point is, if you're aware that nobody makes you use a mock or makes you use a fake or makes you use a real thing, at each step, you can decide your own trade-offs. How fast will it be? In general, mocks will be faster. And if we're talking about a high level, the dependencies, the immediate dependencies, will be ones your team owns. So presumably, you understand very well how to mock them. Or if we're starting to talk about a large enough team that not everybody's familiar with every corner of the system, then you can decide that the subset of the team that's responsible to release a reusable middle-level module is also going to release and maintain the fake of it, like I said previously for external stuff. It applies, if your team is large and structured enough, it applies inside your team as well. So you pick your subject advisedly. And this is one example. Depending on what all is going on, I decide I'd better mock MLB because I really understand it very well and I need that part to be very fast. But MLC, I want to use the actual one and use the actual version of the adapters as well, one with a fake and one with a mock. Now, it depends, of course, on what all I'm doing is take a DNS. Can be anything from looking up an A record, big deal. I mean, if you know the API, it's trivial work. But if you look at today's DNS, it does everything, including the kitchen sink. It could be storing and returning and updating mysterious text records for security purposes. If that is the DNS functionality you depend on, you'd better test it much more carefully than for a simple A or quad A lookup. So this is one example implementation, and this is the way. Note that it doesn't seem to be reusable here because you see body of tests only one, but the point is this is one setup of one example. You would have others. For example, you would probably have a pure unit test for HL beta where both of the middle level dependencies are mocked, but it would use the same body of test. The point of the body of test is making sure you're thoroughly exercising the code of HL beta itself, which is actually the work of unit tests, as we always said. Assuming all external dependencies are perfect, and I understand them perfectly and use them perfectly, how's my logic? That's why the body of tests is reusable. So how to, in this case, I say you have a mock for MLB, you have a fake for the DB, you have a, so you populate it, and you have a mock for the DNS. Now, given we mentioned, we only used mocks and fakes here, but I mentioned earlier when referring to Martin Fowler, yeah, Martin also considers dummies, which are placeholders which do absolutely nothing. I've never really found any sensible situation in which I would use those. So I'm only using mock, actual, and fakes in this context. Pluses and minuses. Mocks are fastest. In almost every situation, a well-implemented mock, like the one in unit test mock in Python 3, are blazingly fast because they essentially do nothing except record how they've been called and return the side effects you've prepared. Using the actual code leaves you the least work to do. You don't have to prepare side effects and things if it's fast enough. And that make sure when you code a reusable module, not top level, that if it has any state, that state can be primed for speed. So if it has, for example, an in-memory lookup table dictionary in which it uses and loads it at start, make sure it can be overridden with a small one for your testing purposes so it can be very, very fast. If a fake is available, it will have to be thorough, it will have to be deep, that is, mimic the semantics of the actual thing very well, and it should usually be fast. Depends on what you're faking, but the typical case where the real service needs to go out over a network, even a fast network, of likely milliseconds, then possibly do some I/O, again, milliseconds, and return. You do it all locally in memory. The milliseconds become nanoseconds, so it's probably going to be fast enough. The problem is that coding it well, even if you understand perfectly the semantics of the real thing, doing the good fake is a lot of work, which is why it should definitely be done by the team responsible for releasing and maintaining the actual thing. Okay, oops, no idea why I suddenly exit. Right, this is the problem of simplicity. I gave the DNS example already, but that's the most detailed. Point is, if you're using all sort of very advanced modern DNS functionality, I really would not sleep well without a fake at my disposal. If I didn't have one, I'd probably carve out the time, extra time, but to have it. If it's an open source thing, as it probably would be, I would contribute it to the original project because mocking all this complexity can become exceedingly hard. You will never gain confidence in that you've actually gotten all the corner cases right. And with any new release of the original, you're back at square one with maintaining your mocks. It's a nightmare. The fake presumably mimics more the thing, so paradoxically, while hard to write in the first place, it's slightly easier to maintain a long time. On the other hand, if I said you're just using A or quad A, translating domain name to IP, that's pretty trivial to mock. Don't need to worry over much. A couple of final issues. But if I'm testing not for correctness, but to make sure that my response times, service parameters, so latency or bandwidth or whatever, don't degrade too badly under heavy load. The so-called load test, quite different from the tests we've been discussing so far are about correctness. Do I have to stick with the old end-to-end thingy? Because how else am I going to measure what time I'm taking, how many computational resources, and so on, if not on a real workload? Well, if you are actually measuring elapsed time and consumed resources, like how much memory, what percentage CPU, and so on, am I taking for this workload? Yes, well, you do need the code paths to go end-to-end. But often, especially for incremental maintenance, you don't need those very heavy things all the way. You can get something like, how much time am I going to spend in code I control? How many times am I going to call external systems? I present it here as if I was only doing one kind of call to an external system, and so just counting number of calls. Obviously, it's more complicated. I'm going to have N1 call to external system S1, N2 call to external system S2, and so on. But for simplicity of presentation, assume that all that matters for time is how many queries to the database, and they all take roughly the same amount of time. In which case, you do see how you can count this, right? Even if you're not actually having a database there, just a fake, that fake can perfectly well, at almost no extra cost, count how many times it's getting called. In the end, the information is there for you to extract. And the time in your code is easily measured if you assume the fake is near instantaneous. Or you determine it, measure its overhead, for example, with time it, and subtract it because you do have n. Now you can compute the worst case total time when you're actually when you will be interacting with the real thing with a simple formula here. And you do need to know what are the service level agreements of the external code I'm using, of course. Otherwise, you cannot offer an SLA yourself if you have no idea how long a system you depend on could take to respond. Because it's whatever it takes plus my little overhead, not very useful. Now, the point is, don't sign a SLA contract based on this, but if you have the measure for an original system and do some changes which you think are optimizations, this kind of partial load test has a big advantage compared with the end-to-end tests, that it runs in a fraction of the time, and if you're paying for your machine time and so on, costs you a fraction of the money. And it gives you at least a qualitative direction. Okay, with this optimization work, am I helping a little, helping a lot, or hurting a little or a lot? And if you do see that it's making things much worse, abandon it and go back to the drawing board. But even if it's improving, but it's improving non-materially, then you know the optimization is not touching the right thing. And this is something that you often observe. People get obsessed, understandably, with optimizing what they can control, their own code. But if their own code does moderate amounts of logic and computation and heavily depends on external systems, if the running of your code is taking 10% of the overall latency perceived by the user, you can make your code twice as fast, and the user will get a 5% improvement, which they won't even notice. So your real focus should be on optimizing that 90%, either cache your result or whatever you can do to make them faster. And this kind of thing, used systematically, helps dissuade excessive pursuit of non-material optimization. And, almost there, refactoring. The base case of refactoring is I have changed the implementation of my module, but it has the same endpoints, same classes, functions, with same arguments, and so on. In that case, that's pretty trivial. The unit tests, or any other test, but might as well do it with the unit tests, should behave exactly like they did before the refactories. Of course, you also want to make sure coverage is maintained. I don't know what your goal is. I tend to be rather aggressive. I'm not really happy with meaningful code if I don't get 90% coverage at least. Some reasonable colleagues tell me 80 takes about half the programming time to get as 90, so that extra 10% is costing too much. But that's a debate you can solve independently of this. Similarly, if the use of mocks and fakes has changed, the test will not pass without adapting accordingly. It's much more interesting to understand how I'm going to test when I've moved functionality. Well, your first thing is make sure your unit test on the module which used to have function X, now doesn't anymore, are failing. If they're not, slap your own wrist and do better unit testing, because obviously you were not exercising that part of the module at all. Very bad unit tests. Now, edit the test bodies and mocks and fakes until everything is passing. And now, with the body of tests, that's one advantage of the reusing part. As long as the body of tests failed at the unit test level, when you're actually checking the logic of the actual model, and mock out everything else, and the mocks and fakes get fixed, now all the higher level that use your code can also validate that your coverage is good and that your refactoring does exactly what you expected it to do. That's even if your module has more state than I would recommend, that state presumably is going to be used, set and used by the higher levels. And last but not least, what about logging? What does logging have to do with tests? The line of reasoning is the following. Unit tests must be fast. And remember that body of test, I want to be reusable, is essentially the heart of the unit test, apart from all the mocking. Not everything can be checked very fast. Some things can. It's a typical problem known as the oracle. Finding a solution is costlier, but checking if something is a solution is fast. So, for example, sorting a sequence is n log n, but checking if a sequence is sorted is order of n because, okay. But that doesn't apply to everything, especially if you're dealing with graphs. Checking that a graph has certain properties, while not quite as costly as manipulating the graph to give it those properties, can still be pretty slow. So could be, for a large graph, costly enough that I wouldn't want it to slow down my unit test. And remember, every other test as well. So what do? I log a snapshot of the status. That's always O of n. I have n nodes and order of n edges. I snapshot or log them. Then, in the background, I run batch jobs to check that snapshot for the properties that are slow to check. I recently started generalizing that to do sometimes samples, because you can't check everything. Depends on how much resources you have. Sanity checks on those snapshots and logs. That is, having determined that the logging of status at some point is cheap enough that I can afford it in the unit test, well, then I probably can afford it in production runs as well. Why not? Because then I can run, maybe sampling, once in a while and check, was everything all right in that run? Do all my sanity checks pass? Does the graph actually have the property I've proven? Remember, one of Donald Knuth's best quotes when he sent to a couple of his peers, I don't know, Dijkstra and Horry, new algorithm he had invented. He had to apologize. Use it with care because I have proven it work, but I haven't tested it. That shows why he's a real great programmer, not just a mathematician. So that's it for my presentation. And questions are welcome, and I hope I have the answers to go with. Apologize if I sit down, but my legs aren't holding up very well.
A standard way of one module using another is to import it. So,
Can everybody hear? Because it
Yeah.
sounds very loud.
so if you have a module that normally imports this other module, say the lower level one, something like that. If you wanted to run that module with a fake, presumably you'd have to have it import the fake rather than import the real one. I can see how you can do that
No.
with system.
The module itself still has the import my real thing. The test has mock patch. Let me show you the code a little bit. Right. When here, for example, when I say mock patch object DBA is the module, DB is the object within the module. That will only work if module dba.py has a statement import db.
Right.
It needs to have an object. It doesn't have to be imported. It could be from foobar import db, whatever. But the point, it needs to have and use an object name that way. And the normal way of getting it is with from or import. Mockpat object reaches into the module, replaces the object named db with the new object named fdb, which is the fake we've just built appropriately.
Right.
So the testing never alters or pollutes the code that you're testing. That's pretty important. It kind of uses a systematic form of monkey patching, which mock patch implements for you.
You mentioned about the overall time, T plus N times SLA something. Now, if you have time-sensitive applications, and you have to go out and connect to different systems, and there's a network problem. Now, with your mock code, everything works fine. As soon as you put it out on the real, like for cloud services.
I do say that you also need the end-to-end. But the point is, when I'm talking about SLA, the SLA does have to include the network if it's a system reached by the network. If some supplier tells you this database has 5 nines availability, unfortunately, it's behind a network which does 2 nines. Then what SLA are they selling you? 2 nines, right?
So actually, I haven't got to my question yet. Sorry. My question is this. Should you have some kind of looping mechanism in your code to say, I'm going to try to loop so many times when I try to do the connect, and if I fail, I abort, and then, in your mock test, it works fine. In the real world, it probably will have to try a number of times. It means my code is going to be looping all over the place.
It's important to test error conditions, and in fact, that's one case where typically you need mocks, or the fake need to be behaving like a mock. My favorite example is the code that does try some operation, except CPU on fire, and the point is that actually lighting the CPU on fire to test things is a bit costly. You burn out all the CPU. And so the whatever is being used in your testing had better have a way to, for example, with mock patch, you'd set side effect to the exception. That then when called, instead of returning a result, it will raise that exception. And one or more of your tests will be of the self.assert raises variety. Now you're checking how robustly does my code deal with failures in code it depends on, internal or external, network or CPU, whatever you need to deal with, you are contractually obligated to deal with. That's not really a load test issue. It's a correctness issue. If your specs say that you need to survive a burning CPU, it's not a point of doing it fast or slow. If your tests say you need to survive a network segmentation, it's a correctness issue. That's no, I wouldn't actually class it among the load test issues. Load test is when there's typically a soft time requirement. You probably wouldn't use Python, but definitely not these techniques if you were developing hard real-time software. That is, 100% of responses must happen in less than 0.8 milliseconds. The 100% part is essentially impossible to guarantee at this level. And yet, there are systems where you need that. But for the vast majority of systems, a normal SLA spec is the kind 95% of queries must be answered within 200 milliseconds. That gives you that 5% leeway that you can use to do checks and retry and check if you can. But again, it's a correctness issue, even though it's expressed in terms of latency.
Hi. First of all, thank you for the talk, very useful. I have a question about test-driven development. I hope it's okay.
During development?
Test-driven development. You mentioned TDD. So in test-driven development, you declare interface of the function, then you write test fails, then you write implementation, right? What should I do if I need to change interface of the function?
So I do not recommend test-driven development unconditionally. Sorry, I spent several pages in my book. My book, by the way, is Python in a Nutshell. The 3rd edition is going to be out any day now, covering Python 2.7 and 3.5. The recommendation I have is specifically when you've discovered a bug. So it doesn't cover the case of the interface of a function changes. When an interface of a function changes, you have a major case of refactoring, really major. Presumably, on hopes, it changes extensively. Previously didn't accept an argument foo, now it optionally accepts an argument foo. The previous code is still correct. If you're doing a breaking change, then you're doing a complete major rewrite of your software, and you should really start from scratch. You're talking about a breaking change or an incremental change?
Yeah, sure, about breaking change.
Breaking change, your existing tests, which are perfect, not only that, but everything your users have done is broken. You'd better start from scratch and hope you still have any customers. TDD doesn't apply at all.
Hello, great talk. I had a small observation. 2 slides ago, I found the slide title a little unclear.
In Q4, is that the check complexity?
No, it's choosing between a mock and a double. I
How to pick a double or actual?
Yeah, and so I don't recall seeing the double.
Double,
ever.
yeah, I could emphasize it more. I mentioned the generic term when I quote Martin Fowler.
It's a stuck double.
Other kind of test doubles. The double is a core thing. At least that's how Martin calls them in.
Right.
It's a rather classical article, so I was hoping the terminology would. And his categorization is dummy, fake, stub, spy, and mock. I don't entirely agree, especially not with Python, but it's close enough. And that's the reference point, since it is a classic article.
All right.
So I need, presumably, to make this clearer to call back, because it is, after all, a slide towards the end of the talk that calls back to a term that has been mentioned only one. Okay. Thank you so much for the observation.
Thank you for the talk. I always struggle when I'm trying to write a code that has some sort of machine learning going on. The issue is that the machine learning code will run through several iterations, and then it will have certain weights, and then my input would sort of generate a prediction based on those weights.
Unfortunately, each ML approach has different behavior in this way. I've done support vector machines. Those are possibly easier to debug than most business code. It's like so easy to get to the multidimensional. Bayesian network, okay, I can do. Deep neural nets, I don't know how to test them. No, seriously, I don't. And that's a pity, because they're the emerging approach with today's power of computation, like TensorFlow and things. I don't know how to test them right.
Right. So actually that was along the lines of my question. So if you're doing a test-driven development, you have to understand what the output would be, but you don't know the output until you've trained the model.
I only do test-driven development when I'm fixing a bug.
Okay.
So I know the output should be the system doesn't crash, for example. That depends. I mean, if I may not know what is right, but I know what is wrong because somebody's reported a bug, right?
Right.
So first, I make sure I get the wrong thing again.
Okay.
With a
So if
test.
my input is being processed and then a prediction is being generated, how do I run an integration test on that? Do I just mock the machine learning component?
Depends on what machine learning approach you're using. As I say, I could, probably not right now, especially not if I have to stand, explain in detail how to do it for support vector architectures and Bayesian networks. But other approaches I've never really grokked in full, and deep nets in particular are unfortunately outside my ken. So I don't know what to. I'm sure we'll have to determine strong ways of checking it, because right now I can imagine that somebody's running the training and then the test, and one test comes out all wrong. Why? How do you fix a bug if you have no idea at the cause? And that often with DeepNet can be the case. I've seen my colleagues, especially in research, but also DeepMind and other branches of Google, who have somehow developed a meta-intelligence, as in, I think we're using the wrong nonlinear function. Oh, why? It tends to do that when, let's try a sigmoid. Okay, and yeah, the bug goes away. To me, it's just as mysterious as, I know what's a sigmoid, don't get me wrong. But why would it change the behavior of the net? Don't know.
Thank you.
Sorry.
So if you have two teams working on components with some sort of dependency between them, and they're both producing fakes, it feels like plugging the fakes in would be a good communication channel between the teams.
Wonderful.
But I don't see anyone doing it or talking about it very much.
As I say, we're doing it for our customers, and of course we don't publish so much what what we're doing internally, but I hope we have... there's no internet connection. Is there Wi-Fi here? Probably not. Anyway.
But I haven't gotten it to work.
Oh, wait. That'd be great if I can. What's a... I do see a LinkedIn guest, but I have no idea.
Can I connect you?
Sure.
Here.
What?
It should be under Romulus 2.0, right there.
Mm-hmm.
Yeah. Here, let me type in the pass. All right, you can type it in too if you'd like.
You go.
For it. Okay.
I don't want to learn that for
randomly
future.
generated, so it's fine.
Okay, so one-off. All right.
Yeah.
Thank you so much.
No problem. Hopefully that works pretty well for you.
Yeah.
Start watching Netflix. That's fine.
Connection was interrupted. Error network changed. I have no idea.
It should be good though. Looks like you're connected still.
A problem.
I can mess with that while you deal with it.
I'm trying to show. This is what we're doing. I was hoping for an essay. It can. Oh no, it's not readable. Oh, I'm sorry.
You're not mirroring.
I need to change mirror. Now I need to set mirroring.
Yeah, here, I'll mess with it. You talk.
I don't know if we've published a blog post or generally explaining why we're doing the beta emulators. But this just explains what we're doing.
That's right. It's on the other section of. Okay, there we go. Mirror.
Okay.
Okay. This later. That.
Right. This is now. This is a reference, really not. Something's fallen down. Not me yet, but not for long. Thank you.
Sure.
So,
It's a clicker, so
what I'm...
probably you don't need that anyway. As your outside presentation.
Thank you. Yeah, I was hoping we'd published an essay beyond the reference. Okay, maybe this one. Yeah. If you want to understand that, if you can't find a reference, I'd recommend you post to any of the Google group asking for an essay about these are called emulators, but it's really the Java, the fake concept made reality for our customers.
So
what we're doing internally, we're probably not going to say, but you can imagine that it's not.
So what I'm thinking is instead of writing a documentation on a new API that's coming, you could just update your fake and then not have that.
I think you should have both because I prefer to have an API, but yeah.
Do you mind repeating the original question?
Sure. It was if you have two teams working on components that have a shared dependency or some dependency, and they're both producing fakes, could you plugging the fakes into each other feels like a good way of communicating between the two teams instead of like writing docs and things like this. Just update your fake. Thank you.
So I was thinking a little bit on your case of if you have a hard dependency on a black box system, does it make sense to record that conversation between the two systems and then replay it? And then if you start to layer on top of that, why would you check your communication between the middle layer and, say, the top layer, instead of just replaying the conversation from the bottom to the top? So if you have that record all the way down, is there value in doing an integration test versus just rerunning the conversation between your different layers?
If the external system is immutable and you never find a test you want to add, and there are many constraints you'd have to analyze. You never refactor, you never add a test, you never, because each of them could produce
A different output.
another example. Suppose what your middle layer needs to do ends up being look up A.com and B.com in either order.
Mm-hmm.
Either order is fine. What you've recorded is one ordering, but it's not part of the semantics. If you choose to check B before A, you're going to end up with two IPs anyway.
But your record's going to be out of order.
The point is the middle system can do things in whatever order it likes. The checks should only come at the end that the things have worked
So this would be a case where you mock out the lowest layer and then you can do your integration test from top to bottom and swap out the bottom layer with the known communication, potentially. So instead
if
of
somehow all the ordering was to be fixed, but I don't see why you'd have that spec.
I think you'll have to think on that more.
In general. The problem is our languages tend to favor this. It's the old problem. I think Dijkstra had an experimental idea, not a fully developed language, whereby used a semicolon to indicate things must happen rigorously, rigidly in this order, and comma to indicate in any order. There is no dependency. It's probably too subtle, but it's true. We always say, even without a semicolon, maybe we just write things one after the other in one per line. We say A, then B, then C. And often it doesn't really matter. Now, when you're recording the sequence of calls, you're recording one sequence and not checking if the sequence is correct. That's the problem. So that sequence will pass, but
then you don't know if you're not testing the output as much as that it said the same thing again. Interesting.
Thank you.
Hello. First of all, thank you very much. It's an honor to be present and then listen to your presentation. So now the question. If you did not have enough time or enough engineering resources, which part of your testing system would you sacrifice, so to say? I don't live in a perfect world, and so my team was very successful implementing a project. So the company had many more projects to be finished. So now we have more projects to deal with, and obviously, we started with TDD, and we were writing unit tests for every single method and every single corner case, and functional tests for every single application. We have this large so-called genomic pipelines that we hooked up with a web front end. And so what we did was that unit tests, obviously, functional tests we called one particular application test, and integration was a whole pipeline in our cases. So after a while, what we ended up doing that, my engineers complained, well, do we have to write unit tests for every single case if we are running functional tests and we are testing the application? And, well, I was like, okay, not write unit tests for everything. After a while, we ended up like, do we have to write functional tests for every single application? And I was like, okay, if the application is basically just a wrapper of a third-party tool, okay, let's omit those. And then we started writing small integration tests with small data that we run before every pull request, for example, and if we merge it to developer branch, then we run large integration tests, and that kind of compensates what we, and it gives us pretty good results. We kind of still catch the bugs if there are any, but what would you do in this kind
The
of case?
last thing I would abandon would be unit tests. Last. Not necessarily TDD. I only advocate TDD in the case where you're fixing a bug. But not, for example, for a feature, for a new feature. That's really a different case than fixing a bug. But if I didn't have unit tests running all the time, my confidence in my code would decrease so drastically. Plus, I've observed it. I've seen it. I mean, I've been called in the past. So before I joined Google, I was a rather well-paid software development consultant traveling all over the world with what was then this new nascent technology, Python. I had just published the Python bestseller, Python in a nutshell, so that made it easy to sell my services to companies experimenting with Python. But I also was well known in other words, such as C++, so I just charged twice as much per hour because I said I had to cover the mallocs if I had to program in C++. Anyway, as is often the case with consultants, I was often called in for projects who had gone way down the tubes. It's like, we just missed our deadline, our major customer is suing us, help. So I tried to help. And invariably, that was a company or a project or a specific team which had incurred far too much technical debt. You're familiar with the term technical debt. Yes. It's like the kind of corner cutting. Used sapiently and moderately, technical debt need not be a bad thing, just like real life debt. I mean, few people buy a house in cash, just very rich speculators. You buy with a mortgage, hopefully with a low enough interest rate, and you pay it over time, and that's a case where debt helps you have a roof over your head. But it's easy to go overboard, and we see the examples mostly in sovereign entities, which borrow to the point where all their revenue goes to pay the interest on the debt they already have, and they don't have the money to fix the potholes. The technical side of things works exactly the same way. If you were just, especially, the point is not incurring it in the first case. It's letting it accumulate because you pay compound interest. No, really, it's a metaphor, but it applies very, very well. If you absolutely need to have a demo at that conference, so you're in a rush to make a certain deadline, okay, fine, incur technical debt, but as soon as the demo is done, as soon as the contract is signed or whatever was the deadline, okay. No, you don't go on to a new thing, you pay the technical debt. You fix things when they're still relatively new and fresh in your mind. Okay. Or you adopt a strategy that I've seen adopted many times, including at successful companies, I have to admit. You just put in a comment, to do, fix this. And there was a beautiful, I think it's KCD cartoon. It shows the Tower of Pisa, and then closes in, the Leaning Tower, yes. Closes in, and there's a post-it with written on it, to do, Giuseppe, fix the foundations.
Good.
That is where you don't want to be.
Okay, thank you very much.
You're welcome.
Hi, thank you for the talk. I have a question about specifically emulating databases. So you were talking about, let's hook this code up to a database that's small, maybe lives in memory and so on. It is often the case that the content of that database really helps you test for a lot of cases. And if you have a production database which may be recording a rich variety of metrics or how the users use the product, in your very, very small in-memory database, you may not actually cover all those cases. So the coverage actually comes from what is in it.
I've never met this case. I've never met the case in which I couldn't, in a couple of megabytes of memory, have all the cases, all the code paths that I need to exercise. Maybe I write code too simple.
So I've had another question then. So you mentioned the terminology that Martin Fowler was using was not always applicable to Python, and testing in Python is a little bit different from Java, for example. Can you give some concrete examples of what you mean by that, and how testing in Python may be different from other languages?
For example, you don't really need to apply inversion of control explicitly. Dependency injection is still useful, but you don't really need to do all the formal IOC because the interface is more often implicit than explicit. Mind you, with abstract base classes, you can. It just, for many cases, especially in the small, it's more formality than it may be worth. That is, it takes almost the same amount of work for you to do it in Python as in Java. Actually, probably more, because Java understands all its verbosity through a huge collection of powerful tools, which, sure, Python has some, but I wouldn't compare, I don't know, PyCharm with Eclipse, for example, in terms of sheer power. There isn't need for that much power if you accept a slightly lowered level of official formality. And in Java, you don't really have the option. At least with up to Java 7, I really don't have any experience. In Java 8, maybe some of the new features let you move a little bit Pythonwards. I just don't know. I haven't written one line of code in it, so.
Thank you.
Thank you.
Hello. Thank you for your talk. My question is, how do you feel about fuzz testing or probabilistic testing?
I've used fuzzing, if that's what you mean by probabilistic testing. That is, fire at my system essentially white noise or slightly colored noise, and essentially just make sure it doesn't crash. I found it precious when I had, it's been a few years, but it happens once in a while when I have to test C++ code. No, seriously, it's not a joke. I'm not joking. The point is that I could crash because of a memory leak. Sure, it could happen in Python, not technically a leak, but I'm just like accumulating so much memory eventually run out. Doesn't really happen much to me. Stray pointer, a wild pointer somewhere, which I'm following through. Again, that's a very C++ specific problem. Languages with safe pointers and garbage collection, which is essentially everyone except C++. Well, okay, there's Rust, but I haven't used it, so I don't know if it's as solid as Java and Go or Python, or risky as C or C. And for those, I found fuzzy useful because I honestly have a hard time if I haven't understood that I'm going to use a pointer that might not be initialized when I was writing the code and then doing a code review and so on. I'm unlikely to have in my body of tests the specific test that will force that specific path of code. If I realize that there are cases in which the path of code ends up using an initialized pointers, I probably would fix my code. And that's where fuzzing helps, because you're simply you can fire an amount of input to your code with fuzzing that's almost unbound, only bound by the computational resources you have to run your thing. And the test is very simply that it doesn't crash. If it does crash, you capture the core dump and find out. Of course, you're recording the inputs that's made it crash. Honestly, I've never felt a need for that and never really used it in Python. Okay, I think we're all done. Thank you so much. It's been a joy. Needs to be turned off.
Yep.